This is lesson 82 on pulse width modulation. In this lesson we'll see how to use pulse width modulation to control the speed of a DC motor and to control the position of a servo. Now the speed of a DC motor is shown here, is determined by the voltage across the motor. The higher the voltage, the higher the speed. And the way you control it is you actually put a pulse width modulated signal across the motor so that the duty cycle of this pulse width modulated signal is determined by duty, that is the amount of time that the pulse width modulated signal is high divided by the period. Is the period. These would typically be maybe a 2 kilohertz pulse train times 100%. So a 50% duty cycle, the duty is high for half the time, which means that the average DC voltage would be half, you see, half of this maximum one, and then the speed would be half its maximum speed. If the duty cycle was 90 or 100%, you'd get the maximum voltage across the motor, therefore the maximum speed. If the duty cycle was, say, 10%, that is, the duty is only on 10% of the time, then the voltage across the motor on average, that is the average DC voltage, would be about 10%, and you'd have a low speed. So that's how it works. Now, in general, you're going to need to use a separate power supply for the motor, because typically the voltage and the current that you can supply from an FPGA board or a microprocessor board isn't enough to drive the motor. And you also want to keep this voltage supply separate from the voltage that you have on your microprocessor or FPGA board. To do that, we typically use a solid-state relay. Here's a symbol for it. There's a little photodiode here. You put a positive voltage across here, so current runs through the diode. This gives off some light. The little phototransistor over here turns on when it receives some light, and therefore the motor, which is connected across here, is shown here. You put the 5 volts coming in here, for example, just like closing this switch, and now you have the voltage across the motor. So that's how a solid-state relay works. This circuit shows how you might set one up. This 5 volts here on your FPGA board, this would typically be 3.2 volts, comes down through the solid-state relay. That's down through this phototransistor. So you want this to be ground. The PWM signal you can bring in here. I show it going through an inverter, so that when the PWM signal is high, this is low, and that actually turns on the LED, and therefore turns on this transistor, and therefore turns on the motor. And when the PWM signal goes low, then the output of this inverter goes high, light goes off, essentially the motor goes off. So essentially you're turning the motor on and off very rapidly to control the speed. Of course, this is like an inductive motor, so it really is the average DC voltage which ends up appearing across the motor. Now, the direction of the motor is controlled by the polarity you put across it. So if you want to change the polarity, you can just change the rotation of the speed, just change the polarity across the motor. And that's usually done with what's called an H-bridge. H-bridge because it sort of looks like an H here. Here I show a 12 volts going across the motor, and this circuit will control the direction and the speed by putting the PWM signal in here. So suppose the direction is high and PW is high, the output of this AND gate would be 1. This inverter makes it 0. I show a normally closed relay here, a normally closed relay here, normally open here, normally open here. These 4 sort of relay symbols would normally be replaced by transistors, but it behaves the same way. So if these 2 are high, this is low, this would be closed. This is high, this is normally open. So that would close this one. So these 2 are closed. inverts here, so you got a 0 here, so this is normally open, so this one's open. This goes through, becomes a 1, normally closed, makes this one open. So with the direction 1 and PWM 1, you have current going down in this direction through the motor. So now, if you make direction 0, then the output here is going to be 0, and now this will be 1, so now these become 1. So in this case, that will close this relay, close this one, open this one, open this one. Now the current goes the other way and the direction of the motor changes. So that's the way an H-bridge works. It turns out that Digilent provides such an H-bridge circuit. This circuit is essentially the one I just showed you, except they use transistors instead of the relay. And you have direction coming in here, and this enable is where the PWM signal would come. This also has feedback inputs, so they provide a couple of inputs here. So if you had something like an optical encoder to measure the position or speed of the motor, you can bring those signals in here. This is ground and VCC on these 2 pins. So this shows what the board looks like. You'd connect the motor across here, and the voltage across the motor you'd put here. Now this one you could have currents up to 2 amps through here. You'd provide the motor voltage supply you'd connect here. That could be up to 12 volts for this particular board. So this is a convenient way to get an H-bridge and be able to control the motor. You'd bring the PWM signal in through here. Now these 2 pins would be these 2 pins on the board, and they plug into these PMOD connectors on the Nexus 2 board, for example. There are a number of these, so that particular one would plug into, say, here, and J1 then would be the direction signal. This J2 would be the PWM signal, and the J1, for example, is connected to pin L15 on the FPGA board, and J2 is connected to pin K12. So you would have to modify your UCF file to give the names, say direction and PWM, and associate directions with pin L15 and say PWM with pin K12. There's a jumper here. Normally you would put this jumper to 3.3 volts, which is what the H-bridge circuit would normally run at. This shows how to control the position of a servo using a PWM. Here's a picture of a servo. There's a cable coming out. It has 3 wires. The white wire would be the PWM signal, and the red and black would be the power and ground. Now, the period of this PWM signal needs to be exactly 20 milliseconds, and then the position of this servo moves back and forth, say plus or minus 45 degrees. There's actually a little DC motor inside this servo, along with a little potentiometer which measures the position, and so there's a feedback circuit in here which reads the pulse width modulated signal and then moves the motor till you get to a particular position. For example, if this is a 1.5 millisecond pulse compared to the 20 millisecond period, so this is a relatively small duty cycle, you see, then this is the neutral position and it just stays fixed there. And then if you reduce the width to say 1.1 milliseconds, then this motor will turn, say, plus 45 degrees, and if you lengthen it to about 1.9 milliseconds, it'll rotate in the opposite direction, minus 45 degrees. So that's how you would control the position of this servo using a PWM signal. Again, Digilent makes it easy to use one of these. You can get a little PMOD connector here For a servo connector, it would actually handle up to 4 servos. This little connector on the servo would plug into one of these, and this pin 1 would be the pulse width modulated signal that would go into one of the PMOD connectors. Again, you should use a separate power supply for the servo. That would be connected to here. It could be a battery or some other power supply. And this jumper you would move to here to make sure that the voltage going to the servo, this VS and ground, that is the red and black connector, get connected to the external power supply.